Steering robots, such as Anthony Best Dynamics SR30, are now used widely throughout the world to carry out vehicle handling tests on the test track. Typically, robots are programmed to provide a defined input to the vehicle's steering wheel, such as a step or sinusoidal input. A robot can do this task much more accurately than a driver. In these tests, the response of the vehicle and the path that it subsequently follows depends upon the dynamic characteristics of the vehicle. The objective of this collaborative project between Ford and Anthony Best Dynamics, described in this film, was to develop a steering robot system to drive a vehicle accurately along a defined path. It was a requirement to do this at high speeds and at high lateral accelerations. To achieve this objective requires the input to the steering wheel to be computed in real time, using feedback from transducers measuring the actual path of the vehicle to close the loop. The steering robot itself has a direct drive torque motor that is mounted to the steering column of the vehicle in place of the standard wheel. The body of the motor is prevented from rotating by a telescopic reaction tube that is fixed between the car's windscreen and the floor. The motor is driven by a sophisticated motion controller which is mounted in a rugged case. This controller is interfaced to a PC that runs the user interface software. A touchscreen can be mounted on the torque reaction mechanism to allow tests to be set up and run easily by the driver. The initial development of the path-following system was carried out using a conventional motion pack containing 3 orthogonal accelerometers and rotational rate gyros. In addition, a 2-axis velocity sensor was mounted to the front of the vehicle. The analog outputs from the sensors were connected to the spare inputs of the steering robot controller, so that the path could be computed by the robot. These transducers give a choice of methods for path calculation, the simplest and most accurate being to use the 2 velocity signals from the velocity sensor in combination with the yaw velocity from the gyro. During the initial testing, it was quickly discovered that the outputs from the velocity sensor were very noisy and were unsuitable for feedback control purposes without heavy filtering. Unfortunately, the filter delay proved to be too great to allow the lateral velocity signal to be used for control. Therefore, for control purposes, the path had to be calculated using the lateral velocity, computed by integrating the acceleration and roll rate signals from the motion pack. A control algorithm was developed, firstly using pure mathematical models to simulate its performance, and then using the actual robot on the test bench. The algorithm uses the heading of the vehicle projected forwards to provide an error signal for an enhanced PD controller. Changing the system to suit a different vehicle requires the fundamental vehicle parameters to be entered. These are tire cornering stiffness, wheelbase steering ratio, yaw inertia, and vehicle mass. A program was developed to generate smooth path definition files for the robot from a simple set of input data. The paths were stored and downloaded to the robot's controller before the test. The system was tested using a variety of paths from a simple straight line to lane changes, slaloms, and circles. As confidence in the system grew, the control algorithm was developed and tuned. There was a lingering problem, however, that of the vehicle drifting off course during the test. This was not an inability of the robot to follow the feedback, but rather an inability of the feedback transducers to measure the path accurately due to integration drift. Results from an ELK test show the desired path, compared with the calculated path from the gyro and forward velocity sensor, showing good path following. However, the actual path of the vehicle shows the effect of the integration drift. What was needed was a system that could compute the path without too much delay and without drift. Oxford Technic TS was able to supply a motion pack with integrated global positioning system, or GPS receiver. The OTS system has a GPS receiver, motion pack, and computer built into the one package. The motion pack has the normal array of accelerometers and gyros which give fast responding signals for computation of the path by the internal computer. This information is then corrected for drift in real time by using the GPS data. Various levels of GPS accuracy are possible, but for our purposes it was necessary to choose the best possible system, which uses a fixed GPS base station connected to the vehicle by a radio link. This gives position relative to the base station with 2 centimeter accuracy. Extensive work was carried out to enable the OTS system to communicate with the robot. A serial communication link had to be developed between the OTS system and robot controller with reliable data transfer at 100 Hz. The advantage of the new system was not only the elimination of drift, but also removal of the need for the external speed sensor. Driving along a straight path immediately demonstrated the accuracy of the new system and that the drift problem was eliminated. With this system, a start gate can be placed on the track and the vehicle automatically led through this by the robot, with the test maneuver being automatically triggered accurately at the start gate. Testing with the new system was an immediate success in both types of vehicle that were tested. All of the maneuvers developed previously could be repeated, with the lateral accelerations of up to 0.9 g being achieved. Repeatability was excellent, as shown by 10 successive runs of a lane change maneuver. This plot shows that the actual paths are indistinguishable. The lateral acceleration traces also overlay very well. The steering wheel angle shows that the input from the robot was consistent, with only a small variation at the end of the maneuver. This could be accounted for by the driver permitting some variation in speed. From the driver's perspective, running a test is simple. Firstly, the driver selects the chosen test maneuver and presses the start button to download the coordinates of the path to the controller. He then gets the vehicle up to speed and heading towards the starting gate. The robot guides the vehicle accurately into the center of the starting gate and automatically triggers the maneuver based upon the vehicle's position from the GPS. The system was tested in low-speed maneuvers, such as a 10-meter radius circle and an elk test. High-speed maneuvers, such as lane changes and slaloms, were also tested. Speeds of over 100 kilometers per hour were achieved with lateral accelerations of typically 0.8 g. We have shown that a path-following steering robot has now been developed for use in repeatable limit handling tests on vehicles. We acknowledge that some further development is necessary to achieve a safe, easy to use and proven system.